the next one actually is from Professor Lili Qiu. Her talk is coping high mobility for beyond 5G cellular networks. Actually, Dr. Lili Qiu is the Assistant Manager Director of Microsoft Research Asia, and is mainly responsible for overseeing the research as well as collaboration with industries, universities, and research institutes. I think she was a researcher at MSR Redmond, and also she was a professor in this Department of Computer Science in UT at Austin, and she is also a IEEE Fellow and ACM Fellow. So please, let's welcome Professor Lili Qiu to give the talk.
Thank you so much, Zhixiong. Hi, everyone. It is my great pleasure to talk about coping with high mobility in beyond 5G cellular networks. Extreme mobility is common in our daily life, such as high-speed trains, vehicles.
Sorry, I'm not sure. Can other guys see the slide sharing? I cannot see it.
Yeah, me too.
Sorry, let me try again. Can you see now?
Yeah.
Yeah.
Okay. Extreme mobility is common in our daily life, such as in high-speed rail, moving vehicles, and drones. Their speed often exceeds 50 miles per hour. Many extreme mobility scenarios require always-on internet connectivity. Today, a common solution to support that is using 4G, 5G, or even beyond. This network has served billions of users and will likely to serve trillions of IoT devices in the future. In this talk, I will focus on two fundamental research problems under high mobility. One is the spatial prediction of wireless channel. Predict a channel for neighboring base stations. Second is predicting the future wireless channel. First, let me take a look on the spatial prediction. Let's first look at how 4G, 5G support mobility today. Consider that we are in a moving train that passes by two base stations. An important decision in mobility management is to determine which base station to connect with and when to hand off to a different base station. This is driven by the wireless quality. It requires a client to measure signal strength from neighboring base stations. And most neighboring base stations are operating on different frequencies. Therefore, it often requires a client to disconnect from the current base station and then connect with a new base station to send a measurement probe to measure the signal strength. So this essentially leads to service disruption and sometimes even connection drops. And this creates the explore versus exploit dilemma, whether we should explore more base stations by paying for such measurement overhead, or explore the limited base station we have seen and use the best out of them. Is the current 4G and 5G reliable under such extreme mobility? Unfortunately, the answer is no. We have conducted a large-scale empirical study of 4G LTE over Chinese high-speed rail, and we found that there are very frequent handoffs at 200 kilometers per hour or above. We require handoff almost every 10 to 20 seconds. Moreover, there are significant handoff failure, often above 10%. This means that network failure occurs at high-speed trains every 3 minutes. And most of these failures are not due to coverage hole, instead due to the limitation of the existing mobility management. And one of the fundamental issues in the existing mobility management is the estimation error in neighboring base stations' signal strength. To overcome this issue, we propose to track the climb movement in the delay-Doppler domain instead of commonly used time-frequency domain. Essentially, wireless signals transmit from the sender and traverse through multiple paths, such as direct path, reflected path, refracted path, and combined at the receiver. The wireless channel can be represented in 3 interchangeable domains, such as time domain, frequency domain, or delay-Doppler domain. In the delay-Doppler domain, the channel representation is consistent of the physical path where each path is associated with amplitude, delay, and Doppler. Consider in this example, we have 2 physical paths between the base station and the mobile on the moving train. And the red path has the attenuation, propagation delay, and the Doppler, each represented by H1, tau 1, V1. Similarly, we have a reflected path. The green path has these 3 parameters. So our goal is to estimate these 3 parameters. Note that delay-Doppler domain is an alternative but equivalent way of representing wireless channel. Like in the frequency domain, the information symbols are now mapped into the 2-dimensional grid, the delay-Doppler plane. Each grid corresponds to a tab with a particular delay and a Doppler shift. The size of the tab is determined by the system bandwidth and sampling frequency. The delay-Doppler domain can be easily converted to a time-frequency signal using the inverse symplectic FFT. Therefore, we can modulate the delay-Doppler signal, and then we use OTFS to modulate the reference signal to estimate the delay-Doppler of the physical parts, and then use the traditional OFDM or OFDMA to modulate the data symbol for backward compatibility. Then instead of paying for this measurement overhead to physically measure the signal from the neighboring base station, what we can do is directly use the measurement with our current base station and then estimate the signal on the neighboring base station without sending any extra probes. This is possible based on the observation that over half of the cells share the same base station but use different frequencies. Therefore, we can just measure the signal from the current base station and extract the multipath profile and then map to the signal on the neighboring base station. So essentially, our input is the delay-Doppler channel impulse response with the current base station, and our output is the delay-Doppler channel impulse response with another neighboring base station. More specifically, what we can do is suppose we have a delay-Doppler representation of the channel matrix with the current base station. Then we can decompose it as a product of 3 matrices. One is the delay orthogonal base, and then attenuation diagonal matrix, and the Doppler orthogonal basis. The first 2 matrices, the delay orthogonal basis and attenuation diagonal matrices, are inherent and fully determined by the physical path. So they are invariant with the different frequency. And only the Doppler matrices vary according to the frequency. And we know the exact frequency used by an alternative base station. Therefore, we can directly compute the Doppler matrices. So essentially, our algorithm perform a singular value decomposition of the original delay Doppler channel matrices with the existing base station, and then we extract the delay and attenuation matrices, and then compute the Doppler matrices based on the frequency used by another base station, so that we can directly estimate the signal with the different base stations. By eliminating the channel measurement overhead with the alternative base station, we can significantly improve the reliability of mobility. In particular, we can reduce the failure in the handoff by an order of magnitude. And also, we can bring the reliability to be comparable to the static and the low mobility scenario. Moreover, we can design simple handoff policy that simply based on the signal strength thresholding, and we can prove that handoff policy is conflict-free. Furthermore, we empirically show that our scheme can significantly reduce the feedback delay, crossband estimation error, and the block error in the data decoding. So far, I have talked about the spatial prediction of wireless channel. Next, let's take a look at temporal prediction. How can we predict a wireless channel in the future? This is very useful in practice because many wireless performance optimization require us the knowledge of knowing the future wireless channel condition so that we can perform rate adaptation, MIMO beamforming, spectral management, and so on. One way to predict wireless channel under high mobility is to use the previous channel and directly predict based on that. How well does that work? To answer this question, we simulate a high-speed real scenario specified in 3 GPP standards. The error in channel prediction is manifest as interference for the signal. As you can see from the figure, the signal to interference ratio rapidly decreases when we increase the mobility. And this is due to large Doppler spread under high mobility. This is the result from 4G, but the results from 5G is even worse because the larger Doppler shift at a higher frequency in 5G. This basically shows that the existing LTE channel prediction mechanism is not suitable for high mobility scenarios. In order to enhance the wireless channel prediction, we propose to predict high mobility instead of the wireless channel. Why? Because mobility has inertia, and this makes it easier to predict. So instead of directly predicting wireless channel, we first estimate the mobility of the physical path and then predict the physical path mobility and map that to the future channel. So first, given the current channel measurement, we extract the physical path property, such as the propagation path length, Doppler shift, amplitude, and then predict the mobility of the future path and map to the channel. Note that it is not easy to directly extract mobility from the channel measurement under existing LTE physical layer. So instead, we again explored delay-Doppler domain channel representation to estimate and predict multipath properties. To do that, we take a closer look how channel estimation works in the delay-Doppler domain. The transmitter transmits a pilot signal, and then this signal will be received at the receiver end and spread across the both delay and Doppler according to the delay Doppler of the physical path. As shown in this example, we have two physical paths, red path and the green path. So in the simplest scenario, the received signal will see two peaks whose peaks position are determined based on the delay and Doppler of these two physical paths. Why do we estimate a delay Doppler of the channel? Because it is physically meaningful, because it directly associates with the path parameter of the physical path. Moreover, inertia is correlated over time, and it's easier to predict than the wireless channel, which has a very complicated multipath pattern. Moreover, it is stable over time, so it requires less frequent measurement. Last but not least, delay Doppler channel is invariant across different frequencies, so we don't need to physically send probe at different frequency to obtain the channel measurement. So how can we estimate a mobility parameter from the delay Doppler channel representation? To do that, we need to address the following challenge. First, we need to estimate the multipath parameters such as the delay, Doppler, and the attenuation. Moreover, we need to determine how many physical paths are underlying this channel measurement. Moreover, we also need to differentiate between the noisy peak versus the real peak. Simple thresholding doesn't work, especially at a low SNR. To estimate the multipath parameter, we formulate a nonlinear optimization problem. And to estimate the number of overlapping paths, we developed an iterative search algorithm. And to differentiate between real peak versus noisy peak, we developed a neural network classifier. In more detail, we formulate an optimization problem to extract a multipath parameter to jointly estimate the delay, Doppler, and attenuation for all the physical paths so that we can minimize the difference between the measured channel and the estimated channel. Note that this problem is non-convex and it's also constrained. So we solve using standard interior point method with good initialization based on the detected peak position and also neighborhood search. Further, we use iterative search to determine the number of physical paths involved. Finally, we remove the noisy peak by developing a neural network classifier. It takes the channel measurement and then it will classify for each of the delay Doppler tab, whether it is a real peak or a noisy peak. And then we eliminate the noisy peak and only feed the real peak into our multipath estimation. Finally, to enhance the scalability of our optimization, we cluster nearby tabs because only nearby tabs interfere with each other. Farther away tabs, they don't interfere. So instead of solving a large optimization problem, we can decompose it into multiple smaller optimization problems and solve them individually to speed up and also improve accuracy. Once we have the multipath parameter for each of the physical paths, we will predict the mobility. To do that, we use the historical path properties in the previous time snapshots. So we need to pair the path measurement from multiple previous time snapshot. And to do that, we use the bipartite matching algorithm. Then Once we pair each of these paths over time, for each path, we can predict its future mobility using a simple standard prediction algorithm such as whole winter or EWMA. Once we have the multipath parameters for each physical path, we can map it to the OTFS channel and then further map it to OFDM channel using ISFFT. How well does it work? So we evaluated using the wireless insight, which is a ray tracing simulator for real environment. We use the real environment from metropolitan city and the campus. Meanwhile, we also use the real mobility traces from our driving and also conduct a USRP measurement. As we can see in this figure, our algorithm is in blue and the state of art is in red. As we can see that we can significantly reduce the estimation error for attenuation, distance, and Doppler shift significantly over state of art. And in terms of channel measurement, we compare with the baseline, which is the standard LTE channel prediction algorithm. And we see 10x accuracy improvement over existing LTE channel prediction algorithm. To summarize, we leverage movement information from delay-Doppler channel representation, and we found that this is particularly useful under high mobility scenario. This is because the movement information is more robust and more predictable. Moreover, movement is invariant across different frequency, so we can predict a channel at alternative frequency without sending physical probes. And we believe that delay-Doppler channel representation can benefit many other applications, such as motion tracking, wireless sensing, geometric modeling. And we hope our work can inspire other researchers to further look at delay-Doppler channel representation. Thank you, everyone, for your attention. I'd be happy to take questions.
Thank you. So if you have a question, please raise your hand. So actually, Professor Chiu, I have a question on the high mobility devices. So it actually, I think 10 years ago, actually we think, okay, it's hard to implement some new technology in our small devices. But now actually we have Apple Watch and maybe Xiaomi Watch, a lot of things. So could you, is that, I think we can realize some new technology like the high mobility technology into our, into our maybe smart wiring devices. So is there any prediction of the industry to catch the, our academia to make all of the technology come true?
I see. So yeah, essentially implying that how were some of the technology developed for high mobility translate to small devices and embedded system or IoT devices? That's a great question. Depending on the specific algorithms, some algorithms are very lightweight. So for example, our SVD decomposition is very lightweight and it can be easily implemented in small IoT devices. And these devices sometimes do need a high mobility support because they can be in a train, on the drone, or even in space. So they will benefit from all the advances on the high mobility support. Did that answer your question?
Yeah. Thank you.
Thank you.
I think we have two audience raise their hands. The first one, Bei Ouyang. Yeah, please go ahead.
Hi, Dr. Chu. So I'm wondering that for the wireless communication, we can take advantage of the multipath to enhance the reliability or the efficiency of the communication. In the wireless sensing, can we also use a similar algorithm or method to either solve the multipath or take advantage of the multipath?
Yeah, that's a great question. Yeah, in existing motion tracking, we are only interested in the direct path. And the assumption is that only the direct path is towards the target. But this assumption may not always be true. Sometimes our target may come from the reflected path. So one of the advantages of our multipath extraction is that we not only estimate the direct path, but also estimate all the multipaths. So it is much more flexible, and also it can enable us to potentially track multiple objects. Some may be direct path, some through from the reflected path. Yeah, so we only scratch the surface here, but I think there's potential of leveraging the path property across all the multipaths to further improve the motion tracking and wireless sensing.
Okay. So do you think the current algorithm you present or other algorithm is enough for the leveraging the multipath in the sensing area, or do we need other methods like hardware or physical layer design to do such a thing?
Oh, certainly. If there's some additional hardware, it will help solving the problem. So basically, what we are solving is a under constraint problem. We have multiple paths and we have some channel measurements. So we are basically trying to derive the most likely path properties. But with some hardware support, we can reduce the number of unknowns so that we can solve this optimization problem much more accurately. So I think, yeah, by combining both software and hardware, we can significantly improve the accuracy of multipath extraction problem.
Okay, thank you so much.
Thank you.
That's all for my
Thank
question.
you. Thank you. And the next one is from Professor Li Mo.
Hi, Lili.
Hi,
Yeah,
Mo.
thank you very much for your talk. Very interesting. And I see that particularly the high mobility and rich multipath environment poses special challenges, right? Particularly the requirement for resolution in time and space. And I see a lot of efforts you've made in addressing those challenges. But essentially, right, this sort of resolution is limited by the signal boundaries and the diversity in antennas. So I'm wondering, have you considered applying some machine learning, for example, reinforcement learning approaches on top of this standard signal processing techniques? So you may actually potentially achieve super resolution with the help of those advanced machine learning tools.
Yeah, that's a great suggestion. So first of all, we are working on for high frequency like a millimeter wave or terahertz. Their channel are more sparse. So the number of unknowns is much more limited. So this optimization problem can be solved more accurately. And secondly, there is the potential of further leveraging machine learning technique to improve the accuracy. I think we are the first work that lay out the problem, and we hope other researchers can further enhance the accuracy and also the application domain of using the delay-Doppler representation optimization of the channel and develop new applications. Yeah, machine learning is definitely an interesting weapon to further enhance and worth looking at.
Right. Yeah. Thank you very much.
Thank you.